Well, first, I want to thank the organizers for this really amazing school. I've been learning a lot from every single lecture. Actually, my first time to IES was exactly 10 years ago at PITP 2014. It's really good to be back. So today I'll talk about non-invertible symmetries. It's a new kind of symmetry that has received some attention in the past few years. This is going to be a series of Blackboard lectures. And because of that, I won't be able to provide a complete set of references during my lectures. So my apologies in advance. There are many related papers that I won't be able to refer to during the talk. So I'll refer you to the papers here for the more complete discussion and the references therein. So the first two lectures will be based on this paper and that paper. And well, actually, my collaborators are also in the audience, Nati Seiberg and Sahang Sefnashri. And for discussions of more general non-invertible symmetry, I refer you to my TASI lecture for many discussions. There are also many other nice reviews on the topic. Okay. So conventional symmetry, as we know, are typically implemented by unitary operator or anti-unitary if we talk about time reversal symmetry. Now, one defining feature of a unitary or anti-unitary operator is that it has an inverse. Just take a dagger. U dagger is U inverse. And that's established by Wigner's theorem in quantum mechanics that every symmetry has to be implemented by a unitary or anti-unitary operator. But the moment we go to quantum field theory in general space-time dimensions, or talk about lattice models in general space-time dimensions, the notion of locality becomes more important. That on the one hand constrains the type of symmetries we want to discuss, but it also leaves room for more freedom of the kind of symmetries that we can have. And that led to many interesting development in the past few years on generalized global symmetries. That includes higher form symmetries, non-invertible symmetry, higher groups, etc. Now today I'll focus on the non-invertible symmetries. There are some examples that I want to give some big overview to start with. But I will only focus on one example in the first two lectures. Perhaps the earliest example is the non-invertible symmetries in the 1+1 dimensional Ising conformal field theory. And just to state the obvious, by CFT, I really mean the continuum field theory rather than the critical lattice model. So we're in 1+1D, that's the lowest possible dimension possible. And Ising CFT, from many aspects, is really the simplest quantum field theory of all. It has the lowest central charge, it has the least degrees of freedom among all the unitary quantum field theory. And already there in the Ising conformal field theory, there's an interesting non-invertible symmetry. So as I say, I won't talk about this example in details. So if this is the first time you hear about it, that's totally fine. In Ising conformal field theory, of course, there's a Z2 global symmetry implemented by some unitary Z2 operator, eta. It's Z2, meaning that if you square it, you get the identity operator. What's more interesting is that in addition to this Z2 operator, or Z2 symmetry, there's another operator. Let me denote it by this calligraphic D. It commutes with the stress energy tensor. In particular, it commutes with the Hamiltonian. So it's a conserved quantity. But it does not obey a group-like multiplication law. If you multiply that operator, which by the way is self-adjoint, let me write it somewhere. If you multiply it by this Z2 operator, it just gives back this interesting operator D. If you squares it, you don't get just one object on the right-hand side, but you get a sum of the identity operator and the invertible Z2 operator. Okay, as I say, if this is the first time you see it, that's totally fine. The rest of the lectures will be self-contained. But I would say this is one of the simplest, arguably the simplest example of a non-invertible symmetry in continuum quantum field theory. There's another example that's quite interesting. That's in the 3+1D quantum electrodynamics, which was discovered more recently. The Lagrangian is very simple. You just have a U1 gauge field coupled to a massless Dirac fermion of unit charge. It's the massless limit of the real-world QED that describes the electron and positron and photon. What happens there is that classically, the Lagrangian has a chiral symmetry. The chiral symmetry famously has an Adler-Bell-Jaqueff anomaly. The conventional viewpoint is that because of the anomaly, this classical symmetry fails to be a global symmetry quantum mechanically. What was realized more recently is that quantum mechanically, it actually leads to an exact non-invertible global symmetry. Even though the two systems are very different, there are actually a lot of similarity between the non-invertible symmetries in QED and the one in the Ising conformal field theory. Now, if you are a string theorist or a conformal field theorist, you might find the first example more familiar. On the other hand, if you are a particle physicist, maybe the second example is more familiar. But to this school and the audience in this school, I will focus on the third example. That is the 1+1D quantum Ising lattice model. By quantum, I just mean it's a Hamiltonian lattice model. And also known as the transverse field Ising model. The Ising model has already been brought up at this school many times. And in today's lecture, we will look at its symmetry from a different point of view. So that's the example I'm going to focus on. But if you are interested in these other two, you are encouraged to look at my TASI lectures, which covers all three of them. Great. All right, so let's jump right into this model. Oh, I should say another thing, that I think the spirit of my lectures will not about giving a comprehensive, a general framework for non-invertible symmetries. On the other hand, I will try to be very example-based. So I will focus on a couple of concrete examples and try to understand the symmetries there to a lot of details. But I think a lot of the general questions are still waiting to be answered and addressed. And I think that's one of the reasons I find this subject exciting and new. So let's talk about the 1+1D Ising model. So my setup is that I'm going to work on a finite chain. And more importantly, it's a finite periodic chain. So I'm going to index my lattice site by J. I have J equals to 1, 2, 3, all the way to J equals to L. And J is identified with J plus L. Now on each site, there's a local Hilbert space, which is just a qubit. And the local operators acting on the jth qubit are just the Pauli operators. We have the Pauli xj, the Pauli zj, and they anti-commute with each other, and they squares to 1. Simple enough. My total Hilbert space will be just a tensor product of all these local Hilbert spaces, which is of dimension 2 to the L. And throughout the talk, I will mostly restrict to this 2 to the L dimensional Hilbert space. Everything we're going to say at the end of the day will be about statement on this 2 to the L dimensional Hilbert space. And that will be extremely crucial for the rest of the discussion. We don't want to make the Hilbert space larger. We don't want to make the Hilbert space smaller. There are some intermediate steps we might want to enlarge it. But at the end of the day, the final statement will be on this Hilbert space. Okay, So I haven't told you the Hamiltonian. The space is discrete. Later, I'm going to write down a Hamiltonian that describes the continuous time evolution. But before I talk about the Hamiltonian, let me first say what are the symmetries I want to impose. So of course, the defining symmetry of the Ising model is a Z2 global symmetry. I'm going to use the same symbol as in the continuum to call this symmetry eta, which is just a product of the x. It's an on-site symmetry, it squares to 1. It cannot get easier than that. And under this convention, z is z2 odd, x is z2 even. In addition to the z2 symmetry, we will also like to impose the lattice translation. You can also write the lattice translation operator T in terms of the Pauli's, but I'm not going to bother you with that explicit expression. So imposing these two invertible ordinary symmetries, the leading order Hamiltonian, you can write down is the standard transverse field Ising Hamiltonian. Because z is z2 odd, so you have to write quadratic terms in z and restrict it to the nearest neighbor interaction. That's the simplest thing you can get. And as we know very well, the phase diagram looks like the following. When G is very large, this term dominates, and then you are in the disorder phase, where the Z2 is unbroken. Up here, you have a unique ground state, and that's just a product state in the G goes to infinite limit. When G goes to 0, you are in the order phase, where Z2 is broken. And you have two ground states there, which splits into these two superselection sectors in the infinite volume limit. So here my convention is that plus and minus are the eigenbases for x, 0 and 1 are the eigenbases for z. Right at g equals to 1, we have the Ising conformal field theory point. All right, so that's a very simple prototypical second order phase transition between a Z2 breaking phase and a Z2 preserving phase. All right, so far everything is standard and has already been discussed many times at this school. Now, the question we would like to address is that usually we say at g equals to 1, by casual inspection, H is invariant under the Kramers-Wannier transformation. So what is the Kramers-Wannier transformation? The Kramers-Wannier transformation says you map your xj to zj, zj plus 1, and zj, zj plus 1 to xj plus 1. And at g equals to 1, you can see that with naked eyes, that is a symmetry of the Hamiltonian. You have a Hamiltonian is made out of some operators. You dictate some transformations on the operators in your Hamiltonian. And if the transformation leaves the Hamiltonian invariant, that's probably a symmetry. But is it really though? The question is the Kramers-Wannier really a symmetry? If you ask Wigner this question, Wigner would say, well, if it's a symmetry, you should probably find a unitary operator that implements the Kramers-Wannier transformation. So is there a unitary operator that does the job? Well, the answer turns out to be no. And the argument is just a one-line argument. And let's go through that. Suppose there were such a unitary operator U that implements the Kramers-Wannier transformation. What would that mean? That means there's a U such that Uxj, U inverse, is Zj plus 1. This is the usual way how an ordinary symmetry transformation, ordinary symmetry operator act on a local operator. It acts by conjugation. But this equality immediately leads to a contradiction. Let's consider U acting on eta, where eta is a defining Z2 symmetry of the Ising model. It's just a product of the xj. But now we can move the conjugation to each individual factor. And turn the xj into zj plus 1. But since we are on a closed periodic chain, each zj appears exactly twice. So when you take the product, this becomes just 1. But that implies your eta is the identity operator. But that cannot possibly be true. Eta is the defining symmetry that acts non-trivially on your 2 to the L dimensional Hilbert space. So we ran into a contradiction by assuming that there were a unitary operator that implements the Kramers-Wannier transformation. Right. Any question at this point? Please feel free to interrupt me anytime. Yes? Why are you finding the Kramers-Wannier transformation like lattice transformation? Right. Right. So you are asking why don't I put J or J minus 7 or anything else? The reason is because for ordinary symmetry transformation, since it's implemented by conjugating the operator with the symmetry operator with the charge, it gives you an automorphism of the operator algebra. If you have an operator A and B, A times B is C, for example, then after the symmetry transformation, A prime times B prime should still be C prime. So this shift in the lattice size is important so that this transformation is still an automorphism. Yeah. Any other question? Great. Also works for anti-unitary U. That's right, yeah. In fact, it works for any invertible U. Right? The only thing you use about this operator U is that it has an inverse. Okay. All right. So we see that there's something ambiguous when we write this arrow. When we write this arrow, you might naively think that there's a unitary operator behind the arrow that implements this transformation. But it turns out not to be the case. So if there were a lesson to be learned from this reasoning, is that we should never write arrow in physics. You don't really know what you are talking about. So the rest of the lecture is about what is the equality behind the arrows for the Kramers-Wannier transformation. And to make that question a little bit more precise, let me write it down here. The question is that, is there an operator such that for the zeroth order condition I would like to demand on this operator is that it's an operator acting on this 2 to the L dimensional Hilbert space. So this is a requirement I almost don't have to say. I want to find an operator within this Hilbert space. I don't want the map that take me from one Hilbert space to another I want to stick to this old Hilbert space. The next condition is that I want this to be some sort of symmetry. So at least I want it to commute with the Hamiltonian. This is not all I ask for symmetry to satisfy, but for the symmetries we're interested in this series of lecture, this is at least a necessary condition. And finally, I wanted to implement in some sense the Kramers-Wannier transformation. The main question is, what do I mean by implement? Okay. All right. Everyone with me on the formulation of the question? Good. All right, now let me see which blackboard I want to use. All right. So before I give the derivation or the complete answer to this question, let me just spell out the answer. And then later on, we can come back and see how to derive it. The answer is that I'm going to define this operator D in the following way. It has many factors, so bear with me for just a second. There's a factor of √2, which you can view it just as a normalization. We can come back to it later. And then there's interesting phase. All right. So that's the operators we want to focus on. Now, it contains several factors, so let's go through it slowly. The √2 is very interesting, but so far it's just a normalization. And the phase is also a normalization to make the algebra looks nicer in the following. For the rest of the factors, the first thing let's notice is that each individual local factor here is actually a unitary operator. It's 1 plus ix over √2. You can easily check it's unitary. So here we're just multiplying a bunch of local unitary operators. And if you multiply unitary operators, at the end of the day, you are still going to get a unitary operator. So let's call that unitary operator UKW. Now this piece, this guy is just eta. So this is a projection operator. Okay. So the claim of Fem of this operator is that it satisfies the questions we ask on the other blackboard in the following sense. When I multiply D with xj on the right, it equals zj plus 1 times D. And similarly, when I multiply D with zj plus 1, that equals xj plus 1 times D. This is very close, similar to the wrong equation we had up here with the U. The only difference is that we couldn't take the inverse of D over there. So even though D, most of it is made out of a unitary operator which has an inverse, at the very end, we multiply it by a projection operator. And projection operator, by definition, has a huge kernel. So this operator is just a big matrix with a 0 eigenvalue. And therefore, it cannot be inverted. So I couldn't move the D to the other side. But that's the reason how we evade the contradiction we have on the left-hand side. All right, any question about the statement so far? All right. So now let me comment on various properties for the individual factor. So one question you might have is that, why don't we just stop at this unitary operator, UKW? That seems to, it's a unitary operator. Why can't we live with it? What's wrong with it? Doesn't it do the job? Well, it's a very simple exercise to do that you can show that UKW, if you act on xj, and by UKW acting on xj, I really mean the ordinary conjugation. This, for most of the site, just gives you zj plus 1. So that seems to fit the bill. But as we know, it cannot be the full story, because if it implements the Kramers-Wannier transformation on every site, you run into the contradiction over there. And indeed, you make a mistake at one site. So when j equals L, this UKW, this unitary operator, maps the local xj operator to something non-local, to something that involves operator on the entire chain. So this is the reason we don't want to work with UKW. I mean, it's a unitary operator, that's great. However, it doesn't commute with the Hamiltonian. But the moment you multiply it by a projection operator, you basically set this factor to 1, and then you reproduce this desired equations. So D, on the other hand, does commute with H at G equals to 1. So this is the tension you have. You either stick to a unitary operator that doesn't commute with the Hamiltonian, so probably you shouldn't call it a symmetry, or you work with an operator that doesn't have an inverse, but is a symmetry of your system. Okay. This UKW has a name, and probably Shay Chen will talk about it in her lecture next week. It's a sequential quantum circuit. So it's a quantum circuit, but it's not a finite depth circuit because it involves a product. It has to be split into several different steps, and the number of steps is linear in the size of the system. It's called sequential because in each step, between each step, the overlap is only one site. But that terminology will not be important for my talk, but it will probably appear in Shay Chen's talk. Okay, any question at this point? Yeah.
In the UK, the ZLZ1, that's the reason why we need a seconds for J to L. So why do we use that?
Good. Yeah, so that's the next point I was going at. So if you look at the expression for the UKW, you pick a starting point, 1, kind of arbitrarily, and then you build your sequential quantum circuit. But as I emphasized, we're on a closed periodic chain, and there's nothing special about the site number 1. And so here we already break that symmetry, that translation symmetry. And also, as you notice, at the very last site, when j equals to L, we didn't have the ZZ term. So we did something different at one site on the entire chain. So this means that this UKW, and you can see that from the explicit action on the operator, does not commute with the lattice translation. When you build this sequential quantum circuit, you pick an arbitrary site to start your product. what is less obvious is that when you multiply it by that projection, this operator actually commutes with the lattice translation. So this projection factor does two things. First, the multiplication of the projection give you the correct action on the local operator. And by action, I mean you multiply the local operator from the right-hand side of D and try to push it through this local operator. It's not by conjugation anymore because you cannot take the inverse. And second, it makes the operator translationally invariant. If you just naively multiply a 1 plus IZLZ1 factor to the definition of D, that would just make it worse. Yes?
Did the projector mean that it's symmetry only in a restricted part of the space?
That's right. So that's another way to say it, that if you only restrict to the Z2 even sector, it's as if there's a Z2 symmetry that exchanges ZZ with X. But what does it mean for the entire system? For the entire system, the point is that we should view it as a non-invertible symmetry. And later on in the lecture, we will see that there are consequences that you will derive from the non-invertible symmetry that you cannot derive otherwise by viewing it as a Z2 symmetry. Yeah?
Is the operator D unique?
Is the operator D unique? Well, I think it's the unique operator that fits the bill here, that implements the Kramers-Wannier, etc. Of course, you can write down many other non-invertible operators. You can write down 1 plus eta. That's an operator, the projection itself. But you wouldn't implement the Kramers-Wannier transformation. I don't really have a proof in mind, but I imagine if you assume there are two such operators, and I guess you cannot take the inverse. I don't have a proof, but I believe it's the unique operator.
Starting point is different, it's the same. J doesn't start on one.
Good. So for the UKW, it's not translationally invariant. So if you start from 1, you get one operator. If you start from 2, you get a different operator. The claim is that take this operator D. It doesn't matter where you start. It's not manifestly obvious from the expression I wrote, but it's a true statement. And later on, I will provide a different expression for this operator where the translation symmetry is manifest. So you can see that this expression has several advantages. Well, first, it's very explicit, right? It's just a bunch of polys, and you can put it into Mathematica if you want to. But it also has a projection operator, makes it clear that it has a big kernel. The disadvantage of this expression is that it doesn't make the translation symmetry manifest. Okay, any other, yeah?
So if you keep G arbitrary and the Hamiltonian is invariant number, the parameter random transformation and G goes to 1 over G.
That's right.
Something like the A square Hamiltonian.
Yeah, so away from G, this operator D doesn't leave the Hamiltonian invariant, but it maps one Hamiltonian to another. It maps the older phase to the disorder phase.
Sorry, so since that in that algebra, if I multiply this X operator from the right, this will conjugate to 1 plus DZ, but 1 plus X, right? But if you multiply this DZ from the left, it seems that it's the sign 2 1 plus X. But only 1 plus DZ. So yeah, I can't realize why that is true.
What is true? Sorry.
So that algebra.
Oh, this algebra. Yeah, it's a very simple. So you can easily verify it using the explicit expression. You just do the unitary transformation 1 by 1. Yeah, this is a unitary, so the way it acts on local operator is very simple. Okay, any other question? Okay. All right, so what are we saying? We are saying that at G equals to 1, the conserved operators, the operators that commutes with the Hamiltonians are eta, T, and D. I didn't give you the derivation of D, but I just told you, I just made the claim that it satisfies all the properties over there. And whenever you have a set of conserved operators, the first thing you want to do is to compute the algebra. what kind of algebra they form. So let's go through that. So for eta is simple, it's just a Z2 operator. For the lattice translation, since I have L side, if you raise to the Lth power, it's 1. And eta is manifestly translationally invariant, so they commute. Now moving on to D. Since D contains this projection operator, we multiply by the Z2, the Z2 just disappears. So we manifestly find this algebra. Okay? Just follows from the projection factor. And that reproduces the algebra in the continuum CFT that I declared in the beginning. And as I said, D times T inverse is the same as T inverse times D, meaning that D is translationally invariant. But the reason I put it inverse here is because this product actually equals D dagger. So we already see something different from the continuum. In the continuum, the non-invertible operator calligraphic D is a self-adjoint operator. D equals to D dagger. But on the lattice, D dagger is not quite the same as D. They differ by a lattice translation by one side. But this is consistent with the continuum picture. How do you go to the continuum? You take L to infinity. In that limit, in the thermodynamic limit, the lattice translation by one side doesn't do much. So the lattice translation operator T becomes 1. And you recover the self-adjoint operator. But if you're on a finite lattice system, D is actually not self-adjoint. And finally, the most interesting equation is probably D squared. And that gives you 1 plus eta times T. So this is not supposed to be obvious at this point. The 1 plus eta factor should be obvious because that just comes from the projection. But you will also find the lattice translation factor. And this is kind of consistent with the intuitive picture here. When you do Kramers-Wannier once, you map an operator on the site to some operator on the links. So it's as if the Kramers-Wannier transformation is a half-lattice translation. But that notion is not precise because on the Ising chain, you cannot really do a half-lattice translation. You only have L sites. What does it mean to translate by half a site? The precise meaning is that you have an operator D that doesn't have an inverse, but when you square it, it's a projection operator times the lattice translation by one side. So this equation is the precise meaning why we can view the Kramers-Wannier as a half-lattice translation in the Z2 symmetric sector. Okay. Any question before I move on to the derivation? Oh, let's see. So in the remaining time, I will derive the expression for D and derive this fusion algebra. And later on, we will talk about its implication on the phase diagram. So to derive it, we have to take a detour to consider slightly different models. And later on, come back to the Ising model and find this expression. So the model we are going to consider is a Majorana chain model. So still, we work on a closed chain. But now on every site, I have a real Majorana fermions. Importantly, I'm going to work with even number of sites. So here is 2L. So my number of sites is twice as large as the original Ising system. And on every site, we have a real Majorana fermion, chi, is a real Grassmannian variable, and they just obey the Clifford algebra. Okay. And since each pair of Majorana fermion will give you a two-dimensional Hilbert space, the dimension of this total Hilbert space is still 2 to the L dimensional because I have 2 L fermions. Now the Hamiltonians I'm going to consider, there are two of them. So I'm going to put a subscript plus and minus. I'm just going to do the nearest neighbor Majorana fermion. All right. So for the plus Hamiltonian, I have the same sign for every term, but I'm also going to consider a different Hamiltonian where I put a minus sign in one of the terms. And you can view this minus sign as putting a defect somewhere on your chain over here. It's a local modification of your Hamiltonian. And the plus sign corresponds to a problem with periodic fermion, with fermions using periodic boundary condition, and the minus sign corresponds to fermion using anti-periodic boundary condition. So I'm going to denote the Hilbert space by H plus and minus, but plus and minus is just a subscript. They're really isomorphic Hilbert spaces. And you can view the H plus as a problem with the periodic fermion, and H minus as the anti-periodic problem. Some of you, many of you must have studied the Kitaev chain model. Now this is slightly different from the Kitaev chain model. In the Kitaev chain, you have the Chi1, Chi2 coupling, Chi3, Chi4, Chi5, Chi6, so and so on. Or you have the other way around, Chi2, Chi3, and Chi4, Chi5, so and so on. Here I have the nearest neighbor interaction between every pair, every adjacent pair. The Kitaev chain model flows to a gap system. That's an invertible field theory. This model flows to a gapless quantum field theory. So the thermodynamic limit is a free Majorana CFT. So the Lagrangian is very simple. You have one real Majorana vial fermion, which is left moving. You have another Majorana vial fermion, which is right moving. And there's no mass. It's just a massless conformal field theory. And you can view the H plus problem corresponding to the, it will flows to the continuum CFT with a periodic boundary condition. And for high energy physicists or string theorists, this is usually called a Riemann boundary condition. And for the anti-periodic problem, for string theorists, that's known as the NS-NS boundary condition. And we'll come back to that later. All right, let's see. So I want to keep this. Maybe I'll bring that up. Oh, I didn't break it. So later on, we're going to relate the fermion problem back to the Ising lattice model. But before that, let's just analyze the fermion problem on its own right. So on the lattice, for this Majorana lattice model, what are the symmetries? There's a fermion parity symmetry -1 to the f. The way you act on the fermion field is just to flip the sign. Okay, so that's obviously a symmetry of both Hamiltonians, H plus and H minus. You can write this symmetry operator very explicitly. -1 to the f is I to the L, chi1, chi2, all the way to chi2L. Okay, you can easily check that that does the job. Now there's something interesting here. When you pick the minus Hamiltonian, there's something special about site number 1, because we put the minus sign between the link, on the link between 2L and 1. And because of that choice, it makes sense to start the product here from 1 all the way to 2L. But if you work with the plus problem, there's nothing special about site number 1. And yet here we choose the site 1 to start the product. If you had chosen site number 2 to start the product, you have chi2, chi3, chi4 all the way to chi2L and chi1. That operator is very similar to this, but they differ by a minus sign because all the chi's anti-commute, and we have even number of fermions. So that is to say that for the periodic problem, there's an intrinsic sign ambiguity in how I define this operator -1 to the f. I can change the sign of -1 to the f, and that wouldn't affect this relationship. So for now, let's just make a choice. Here, I make a choice of putting a plus sign here and start the product with chi1. The phase here is just to ensure that if I square the operator -1 to the f, it's +1. But the real issue is the intrinsic sign ambiguity, and we will see more of that in just a minute. What is big F? It's part of the name. So this operator, you should view this operator as, this is the name I put it to the operator. This is, I think this convention is, this is more convention in the string theory literature, yeah, where F is the fermion number. It makes sense when you have a system where you have a U1 symmetry that counts the number of fermions. So when F is odd, you have odd number of fermions, and this gives you a minus sign, and vice versa. Yeah, it's the fermion parity, yes. Any other questions so far? Okay, so that's the first symmetry. The other symmetry we want to consider is the Majorana translation. So I'm going to call this operator T plus for the periodic problem. So you just shift your fermion by one site. But notice that this is the Majorana site. So I'm using different symbols to label the Majorana site versus the Ising site. And this operator is not a ZL symmetry because since we have 2L sites, it's 2L power is 1. It's obviously a symmetry of the H plus problem. For the H minus, for the anti-periodic problem, at first sight, you might think there's no translation symmetry anymore because we flip the sign on one of the links. But if you think about it a little bit more, there's actually a symmetry. Let me write it here, T minus. Such that it's chi L plus 1 for most of the site. But for one site, you flip the sign. And that will still commute with the Hamiltonian. Okay. So these are the symmetries we have on the lattice. In the continuum, however, what are the symmetries we have? We have one left-moving Majorana biofermion. We have one right-moving Majorana biofermion. So obviously, we still have the -1 to the F symmetry, which is flip the sign of both fermion fields. But in addition to that, we also have a chiral fermion parity, which I call -1 to the f left. This guy only flipped the sign of the left moving fermion. But leave the right moving fermion invariant. So if you just look at it, it seems that there's a mismatch in the number of symmetries. In the continuum, clearly we have a Z2 cross Z2 internal symmetry. You have two fermions, they don't talk to each other, you can flip their sign independently. But for the lattice system, we just have one Z2 internal symmetry, and we have some lattice translation. So the way it works is that this Majorana lattice translation symmetry is actually related to the chiral fermion parity. And the way to see that is just to solve the spectrum explicitly. When you solve the spectrum, it roughly looks like this. This is just a quadratic fermion system. And the function is just sine pi k over L, where k is an integer for the periodic problem and k is a half integer for the anti-periodic problem. And you have two regions, two zeros here. This is 0, and this is k equals to L. From one end, you get the left-moving fermion mode, the side left. From the other end, you get the right-moving mode, side right. But since here you're halfway through the Brillouin zone, when you do a lattice translation, the t there, you get the extra minus sign. You get a relative sign between the two modes. So if you take the lattice translation and match that with the symmetry in the continuum, you get a relation like this. Where P is the momentum operator of the continuum CFT. So the lattice translation implements some small translation in the continuum, but on top of that, there's a relative minus sign between the left moving and the right moving mode. So this is how the symmetries match. And you kind of expect this has to be the case because -1 to the f left is a chiral fermion symmetry. And chiral symmetry in fermion theory is notoriously difficult to realize on the lattice. And here, the chiral fermion symmetry is realized via a lattice translation in this Hamiltonian system. Okay. So now let's look at the algebra between these symmetries. You know, whenever we have a set of symmetry, we should try to compute its algebra. This is a very simple calculation we can do in real time. Let's just compute t plus -1 to the f, t plus inverse. Now recall that -1 to the f is I to the L, chi1, chi2, all the way to chi2L. The lattice translation just move chi1 to chi2, chi2 to chi3, chi2L to chi1. But then you want to rearrange it into an expression that looks closer to the one you started from. So you want to move chi1 all the way to the leftmost. But you have odd number of fermions in front of it. So you get an important minus sign here. On the other hand, if you compute t minus with -1 to the f, because of the extra minus sign you have here, they end up commute with each other. And this minus sign is reflected in the continuum field theory. Let's see, I need to keep this. In the continuum field theory, if you are in the Raman sector, the canonical quantization of the free field theory shows that -1 to the f and -1 to the f left, anti-commute. Whereas in the NS-NS sector, in the anti-periodic sector, they commute. In the continuum, this minus sign corresponds to an anomaly of the Z2 cross Z2 symmetry. On the lattice, it's a little bit more subtle because you can view it as an anomaly involving the lattice translation and the fermion parity. But you faithfully reproduce this minus sign on the lattice. In the continuum, this anomaly is actually a mod 8 anomaly, meaning that you have to have 8 copies of the fermions to trivialize the anomaly. But the minus sign only captures the mod 2 part of it, and the lattice only see the mod 2 part. Okay, so what do we have here? We went through a fermion lattice model. It has a fermion parity symmetry. It has a Majorana translation symmetry. Even though both operators are very elementary, there's an interesting minus sign in the algebra between them, which signals an anomaly of an internal symmetry in the continuum Majorana CFT. Now, why did I go through all the discussion about the Majorana CFT? That is because usually in classroom we say the Majorana CFT is related to the Ising mod. So we should be able to understand all the symmetries of the Ising model from the Majorana system. And the reason we usually say Ising model is the same as the Majorana model is because we can do the Jordan-Wigner transformation. So in the Jordan-Wigner transformation, you write it fermions in terms of the spin variables. And you can easily check that this change of variable is consistent with the algebra on the two sides. Now, if you plug in the Hamiltonians for the fermion fields, write it in terms of the spin variables, you'll find you recover the transverse field Ising model in most of the site, but at one link, you will make a mistake. Where -1 to the f, if you write it in terms of the polys, it's just a product of all the sigma x. Okay. So that means globally, the Majorana model is actually not identical to the Ising model. There's one term that doesn't quite match. For most of the terms, they do. But in this term, the original Hamiltonian is local in the fermion field. It only involves nearest neighbor interaction. But in this term, it involves the sigmas, the polys, on every site. And this is to be expected. You don't expect the two models are globally identical. If they were globally identical, you run into a contradiction. In the Majorana lattice model, you have a Z2L symmetry. That's a Majorana translation. But you don't have a Z2L symmetry in the Ising model. On the Ising model, you only have L site. So there's something, the relation must not be a literal equality. There must be something more to it. Any question to this at this point? Yes. why that minus sign means an anomaly. So let me explain that in the continuum. So I stated as an anomaly in the continuum. So in the continuum, what is an anomaly? Anomaly is an obstruction to gauging that Z2 cross Z2 symmetry. When you try to gauge it, you have to turn on all kinds of symmetry backgrounds. So there will be a case where, so you first have to sum over these two sectors. You have to sum over different boundary conditions. But when you are in the Riemann, namely the periodic boundary conditions, because the two symmetries don't commute with each other, there's an inconsistency when you try to sum over their background fields. Another way to say it, perhaps more elementary way to say it, is that in the periodic sector, when you gauge the symmetry, when you gauge the symmetry, the first thing you do is to project to the gauge invariant operators. If you have two symmetries A and B, such that AB equals minus BA, this algebra doesn't leave any state invariant. So there's just no state that's invariant under both A and B. So you fail at the very first step of gauging. And therefore, that can be understood as an anomaly. Okay, any other question? Okay. So because of this single term, we know that they are not literally the same. The precise relation is that you can view the Ising model as Majorana model, but you gauge the fermion parity symmetry. Now, I could spend some time talking about gauging a symmetry on the lattice and in the continuum, but let me first just tell you the final outcome of this gauging procedure. I'm going to state it on the lattice, but the statement will look very familiar to those of you who have studied gauging in continuum CFT. So here we're going to minus 1 to the F. So you can do the gauging in the usual way, namely you introduce gauge fields on the links, and then you impose Gauss law, and you try to solve most of the Gauss laws and write the final Hamiltonian in terms of the new variable. And the final outcome you obtain from doing that boils down to these two steps. In the first step, you take a direct sum of two systems. And that's the reason I have to talk about both the periodic and the anti-periodic problem. The two problems differ by inserting a fermion parity symmetry twist. You change the boundary condition using that symmetry for minus 1 to the F. When you gauge it, you have to take both of them into account. So in the first step, you take the direct sum of the Hilbert spaces for the two problems. Each one of them is 2 to the L dimensional. So this direct sum Hilbert space is 2 to the L plus 1 dimensional. And in this bigger Hilbert space, you just put the Hamiltonian to be H minus in this block and H plus in this other block. Okay. So in the first step, we temporarily enlarge the Hilbert space by a factor of 2. In the second step, you do a projection. And you can think about this enlargement of the Hilbert space as adding a new Z2 gauge field on one of the link. In the second step, it should be more familiar. It's just when you gauge any symmetry, you should project to the symmetry invariant sector. But here, there's a little twist. We're going to project minus 1 to the F, the symmetry we are gauging, to plus 1 for the anti-periodic problem, but to minus 1 in the periodic problem. Now, this looks familiar, right? You just project to the Z2 even sector when you gauge the symmetry. This minus sign might look a little bit unsettling at first sight. But remember, the sign choice for -1 to the f for the periodic problem is intrinsically ambiguous. There's no reason why we started the product of the fermion fields from site number 1. If we had started from site number 2, you get a relative minus sign. Another way to say it is that you can actually put +1 or -1 here. You'll get the same answer. It's just that for the matter of presentation, doing the -1 is easier. Now, for those of you who have studied string theory, you will know that these two steps are exactly what we did when we performed the GSO projection for type 0 string. In type 0 string, you have a sign choice in the Riemann sector that will correspond to 0a and 0b. So both choices are legitimate, but for the presentation, it's easier to pick this. All right, any question about this point? So in the first step, you make the Hilbert space larger, but in the second step, you do the projection. So the Hilbert space reduces down to the original size, 2 to the L dimension. So the final Hilbert space is a projection of this big Hilbert space by a factor of 2. And this is again 2 to the L dimension. Now, why do we do these two steps? You see, the term we were bothered by is this guy. This guy doesn't look local. But now, if we are in the anti-periodic sector, so we're choosing the minus sign here, we project to the -1 to the f equals to +1 sector. So this whole thing is a minus sign, the same as the rest of the term. On the other hand, if we are in the periodic sector, we pick the plus sign here, but then we project to the minus eigenvalue sector. So this whole thing is again just a minus sign. So we again have the same sign as the rest of the term. So after this two-step procedure that you get out of gauging, you find the Hamiltonian, you find this big Hamiltonian equals the one for the transverse field Ising. So this globally relates the Ising model to the Majorana model. Okay, so now with this preparation, we are finally able to answer or to derive this operator D. So the name of the game is that we want to track what happened to the symmetries in the Majorana system when we transport them to the Ising model. For the -1 to the f, it's gauged, so let's not worry about it. There's going to be a dual symmetry, and that's the eta Z2 symmetry, but that will work out just fine. The tricky question is what happens to the Majorana translation? So naively, you can define operator T tilde. Everything with the tilde acts on the bigger Hilbert space. You can define it to be T minus, T plus, and you put 0 on the two blocks. Right? Remember, we have a different Majorana translation operator for the anti-periodic and the periodic problem. However, this operator doesn't survive the projection. It's a legitimate operator at step number 1, but when you try to go to step number 2, because T plus doesn't commute with -1 to the f, it doesn't act within that projected Hilbert space. If you take the square of it, then there's no problem. The sign disappears. In fact, indeed, this operator, when you restrict to this 2 to the L dimensional Hilbert space, is just the Ising lattice translation. So that explains why, even though in the Majorana problem you have a Z2L symmetry coming from the translation, when you go to the Ising model via gauging, the Z2L disappears. You only have the ordinary lattice translation of one Ising site. But if you think about it a little bit, we're being a little bit too harsh, right? The reason that this operator T tilde doesn't act within the projected Hilbert space is because T plus anti-commutes with the projection operator minus 1 to the f. Right? It's because in the algebra, where is it? There. It's because of this minus sign. But T minus did nothing wrong. T minus commute with minus 1 to the f. So if you define an operator that only has T minus, which commutes with the projection, but put a big 0 here, this operator will totally survive the projection. And let's give it a name. Let's call it D, and with a factor of √2. It acts within the projected Hilbert space, and therefore it becomes a symmetry of the final Ising model. And this, I claim, is exactly the operator that I wrote up there in terms of the spin variable. And the fact that we put a big 0 here is related to the fact that there's a projection operator at the very end. And from this expression, it's also clear when you square the operator T, you get T minus square here, but that's just the lattice translation of the Ising model times the projection. So this presentation makes the one of the fusion algebra, E squared equals 1 plus eta times T manifest. Okay, yeah, so I think I'm right on time because I finished the derivation right here. And next time I will provide some other presentation for the operator. In particular, we will spend some time talking about the matrix product operator expression for this operator D. All right, I'll stop here.
Any questions? Yeah.
All the models that you're about with that would be non-invertible. Are there graph models?
Yeah, so I will talk about that next time. Yeah, that's a great question. And the answer is yes, there are.
Okay, I don't see any other questions, so let's go to dinner.
All right.